As an illustration of the power of the Wronskian, let's try to solve a second order differential equation using Lagrange's method of variation of constants. So I have a second order differential equation y double prime plus p of x y prime plus q of x y equals f of x. Just about any horrible looking differential equation can be cast in this form as long as it's linear. So it's a linear second order differential equation. Now we assume that we know the answer to the problem of what happens when f of x is equal to 0. That's called the homogeneous problem. So assuming that we know the homogeneous solutions to this equation, in other words, we have y homogeneous x is equal to a linear combination of c1 y1 of x plus c2 y2 of x. So that's supposed to be known through other methods. And once we know that, let's try to find the particular solution to the problem of having f of x to the right side. So that's called the general solution, and that's called the particular solution. And the final solution for this is going to be the combination of the homogeneous and the particular solution. So our aim here is to find the particular solution. So I'll not bother writing p of x, q of x, f of x anymore. I'll just write it as p, q, and f, assuming that you keep track of the functions. Now we're also going to presume that the Wronskian w formed from y1 and y2 are not 0. In other words, y1 and y2 are linearly independent, which it has to be, otherwise they will not be solutions to the homogeneous equation. So we already know that this must be true. All right, now how do you find the solution to that? Lagrange's method, or Lagrange's ansatz, is the following. Lagrange assumed that all you need to do is make c1 and c2 functions of x, and then this will be the particular solution under certain conditions. So the purpose of this video is to find those conditions and perhaps explore a simple example. So Lagrange's ansatz is that y of x, the particular solution yp of x, must be c1 of x, y1 of x, plus c2 of x, y2 of x. And this is supposed to solve the full non-homogeneous equation. Let's take the derivative. I'll not write yp anymore. Y prime is going to be, well, let me write yp prime is equal to c1 prime y1 plus c1 y1 prime, because I'm using the Leibniz rule there. Similarly for the other term, c2 prime y2 plus c2 y2 prime. Now we're going to assume, and we'll justify this after we finish the calculation, we're going to assume we have enough freedom to set c1 prime y1 plus c2 prime y2 equal to 0. Let's just do that and see where we get. So that's where you get your name tagged onto a method when you have the courage to do something like this. So yp prime then becomes simply c1 y1 prime plus c2 y2 prime. Now we'll differentiate it again. Yp double prime is equal to, playing the Leibniz rule game, on that first term, and now on the second term, now at this point you notice that I can use the homogeneous equation, because this so I won't write this as p. I want to keep this general, so I'll just write it as y, and later on we'll write the particular solution after taking out the homogeneous solution. So I'll just remove the p subscripts here. What I'm going to do is I'm going to put this in the homogeneous in the non-homogeneous equation, because we want this in the non-homogeneous equation. The reason I removed the P designation is when you substitute this in the non-homogeneous equation, you will find that the homogeneous is already there. So let's put this back in the load, and we're going to get, let me write down the load again, y double prime plus py prime plus qy equals f is the load. And let's substitute what we have here. For y double prime, I'll substitute that. For y prime, I'll substitute this. And for y, I'll substitute just y. So I'm going to get, for y, I'll substitute this. So let me see what I get. C1 prime, y1 prime plus C1, y1 double prime plus C2 prime, y2 prime plus C2, y2 double prime. That's just the first term. And then P times y prime, which is going to be C1, y1 prime plus C2, y2 prime, and then plus Q times y, which is simply that, C1y plus C2y, where C1 and C2 are both functions of x, so don't forget that. And all that is equal to f. Now let's just group together constants C1 times things. C1 has got y1 double prime plus py1 prime plus qy, and C2 has got y2 double prime plus C2 p y2 prime plus q y2. Okay, and then you have these standalone terms which we have not yet done anything with. So C1 prime, these are the prime terms with the primes on the C's, plus C2 prime, y2 prime equals f. This satisfies the homogeneous equation. y1 satisfies the homogeneous equation, y2 satisfies the homogeneous equation, so those two things are 0, leaving us with the second equation, and the second equation is C1 prime, y1 prime plus C2 prime, y2 prime equals f. Now, this may all look very complicated, but in reality, it's just two systems of equation. This is like saying, ax plus by equal to 0, and then it's like saying that cx plus dy equals f, where a is equal to y1, b is equal to y2, c equals y1 prime, and d equals y2 prime. The only big deal about this system of linear equations is that the coefficients themselves are functions of x. But an x and y in this analogy is going to be c1 prime and c2 prime. So we are solving for x and y. Back to Cramer's rule. There's nothing more to it than that. So c1 prime by Cramer's rule is the coefficient matrix. This time it's 0f, y1, it's y2 prime, divided by the Wronskian, because the Wronskian is this one. And c2 prime, likewise, is y1 prime, 0f, divided by the Wronskian. So this is a very elegant method, and once you find c1 prime and c2 prime, you can find c1 and c2 up to a constant. That constant is very important because that constant is going to give you the homogeneous solution. So let's examine all this in practice, and let's take a very simple example to see how the guts of this method works. So let's try the example y double prime plus y equals x. Now the good thing about this example is that you've probably beaten the homogeneous solution to death in earlier courses. So y double prime plus y equal to 0. How do you solve this? Well, you use the Euler-Ansatz. Y equals e to the prime means with respect to x, by the way. So it's going to be e to the lambda x. And so when you substitute this is called the Euler ansatz. Then I'm going to get lambda squared plus 1 times e to the lambda x equal to 0. E to the lambda x cannot be 0, otherwise there's nothing to do. So that's called a trivial solution. So for non-trivial solutions, you need lambda squared plus 1 equal to 0, which tells me that lambda equals plus or minus I, which is the square root of minus 1. Well, once you have that, the solutions are going to be y1 and y2 are going to be linear combinations of e to the ix and e to the minus ix. Well, you don't want to play with complex numbers too much, so what I'll do is I'll take the linear combinations of e to the ix and e to the minus ix instead. So those are linear combinations of sine x and cosine x. So we have our y1 and y2. Let's call y1 equal to cosine x and y2 equals sine x. And those satisfy the homogeneous equation. And if you want, you can readily verify that. When I take the double derivative of cosine x, I'm going to get, first I'll get negative cosine x, negative sine x, and then I'll get positive cosine x. I'll get negative sine x and then I'll get negative cosine x. Well, if I add negative cosine x and positive cosine x, I'll get 0. So it satisfies the homogeneous equation. For sine x, I'm going to get, when I take the first derivative, I'm going to get cosine. When I take the second derivative, I'm going to get negative sine. And negative sine plus sine is also 0. So that also satisfies the homogeneous equation. So that's just a good verification. Let's form the Wronskian next. This Wronskian will then be used to find C1 and C2 for the full solution. So the Wronskian is just, remember what it is. It's y1, y2, y1 prime, y2 prime. So differentiating cosine, so let me first write cosine and sine. Differentiating cosine gives me negative sine, and differentiating sine gives me cosine. Well, that's great, because cosine squared plus sine squared is 1. So the Wronskian is just a very easy thing in this case. Oftentimes that's not the case. Unfortunately, in your homework, it won't be the case. So you have to deal with some more complexity. Let's find out what C1 prime is. C1 prime would be 0f, which is this thing here, sine x. I would just stare at the Wronskian all the time. So in this first column of the Wronskian, substitute 0 comma f. It always is 0 comma f because that's the assumption we made, and that's f. So this sine x cosine x divided by the Wronskian, which is 1. So let's see what this is. I get 0 negative x sine x. Then I integrate that. If I integrate negative x sine x, I get C1, which is negative integral x sine x dx, plus C1 naught. Now this integral can be done using Eulerification or Euler's trick. I won't bother wasting time doing that. I just want to show you that this, in principle, it works. Similarly, let's find out what C2 is. Or as a matter of fact, maybe I should just tell you what it is so that we can enjoy the fruits of our labor. You can use the Euler trick to find it out, but I'm just going to tell you what the solution is. This is going to be x cosine x minus sine x plus C1 naught. Now C2 likewise, C2 prime likewise is cosine x, the first column of the Wronskian kept the same, minus sine x. The second one is 0x divided by 1. And this would be x cosine x, which means that C2 would be the integral of x cosine x dx plus C2 naught. That's why the Euler method is so good. If you use the Euler's trick and write this as imaginary part, then this can be written as a real part. So in one step, you can get both these integrals. I've shown these details in the example in the notes. You can look at that. And so this will end up being, C2 will end up being cosine x plus x sine x plus C2 0. Now that we have C1 and C2 as a function of x, we can put back and see what the full solution looks like. It's worth looking at that. The full solution, y of x, would be C1 of x, which is this thing here, times cosine x times the first solution, plus C2 of x, which is cosine x plus x sine x plus C2 0, times the second solution, which is sine x. A lot of the things will disappear actually. If I try this, I get x cosine squared x minus cosine x sine x plus C10 cosine x. That's your homogeneous solution right there. So the homogeneous solution has reappeared thanks to the constant of integration while finding out C1 and C2. And here I have cosine x sine x, which you'll notice cancels, and then plus x sine squared x plus C20 sine x. And that's your other homogeneous solution. And then I have x cosine squared x plus x sine squared x, which is 1. So the full solution to this problem, the full solution is the homogeneous part, which is C10 cosine x plus C20 sine x, plus the particular solution, which in this case is just x. Now you may think, oh, I could have guessed that without doing any of this work, but in more complicated problems, it's not an easy thing to do.